we will go to next. This is the last lecture. The title is Simulation of Airfoil Bearings for Use in Turbo Compressor Applications. This lecture is by Mr. Willingham. Mr. Willingham is a student of Wilson School of Mechanical, Electrical and Manufacturing Engineering from UK.
Hello everyone, my name is W.l Heaps and I'm a recent mechanical engineering graduate from Loughborough University, Leicestershire in the UK. The work I'm pleased to present to you today at the 2021 International Conference for Advanced Vehicle Powertrains is a study on the simulation of air bearings for turbo compressor applications, specifically focused on airfoil bearings. This was work completed by myself and colleagues at Loughborough University, Harry Quester and Dr. Mahdi Mohammed Bor, as well as with the help of Dr. Stephen Boucher and Professor Gunther Offner of W.l Heaps GmbH, based in Graz, Austria. To begin the presentation today, just an overview of what I'm going to present. Firstly, an introduction on the significance of this study, its context and place within the wider engineering community. Following this, a short introduction on airfoil bearings, their architecture and characteristics, followed by the aims and objectives of the project. After this, we have the methodology applied, simulation workflow on how the data was gathered, the results generated during this project, some key takeaway conclusion points, and finally, novelties seen and contributions to knowledge brought about by the project and study. So the introduction. The internal combustion engine provides around 25% of the world's power, things such as electricity generation, or perhaps more relevant to this conference, transport and vehicle applications. The obvious caveat with the traditional internal combustion engine is that it produces large amounts of greenhouse gases. On a global scale, this currently sits at around 10% of the global greenhouse gas emissions produced. Now more than ever, there is a great need to develop technology to reduce the impact the IC engine has on the environment and on human health. This has been highlighted times in the news over the years, more recently in the UN report generated through the Intergovernmental Panel on Climate Change. This can be achieved through the optimization and efficiency and performance of the internal combustion engine and powertrain solutions. Turbocharging is one method through which emissions can be lowered while also increasing power output and performance of an internal combustion engine. Most commonly, in the past, turbochargers have utilised floating ring bearings, which can be a source of noise and also mechanical losses, as well as requiring large cumbersome oil feed systems. By replacing these airfoil bearings, the overall efficiency of the turbocharger and internal combustion engine can be increased. Therefore, an overall improvement in fuel economy and reduction in emissions would be experienced. Through the proper application of engineering software, huge savings in both time and money can be made, as the need for expensive prototyping and physical testing is greatly diminished. Now just moving on to airfoil bearings themselves. These components are composed of a spring-like mechanical foil structure, which can be seen in the diagram on the left. By generating a hydrodynamic air wedge when the rotor is operational, there is no need for oil lubrication, and as a result they display clean operation and high speed capability, with clean operation presenting the opportunity for use of these components in hydrogen fuel cell applications. The individual bumps which the foil is comprised of experience friction against the housing when under deflection, allowing further energy dissipation and increase in stability. The aims and objectives of the study are as follows. Create a numerical bearing model within MATLAB or the bearing maps, from bearing maps. Explicitly link the bearing model into Excite Power Unit to create a flexible multi-body dynamic turbocharger system model. Following this, perform analysis on the dynamics of the system and determine the point of resonance and the role body flexibility plays in the system dynamic response. The software versions used during the study can be seen displayed at the bottom of the slide. Now on to the methodology. Bearing maps were taken from a previous study which used an analytical perturbation method to evaluate the stiffness and damping coefficients of an airfoil bearing. This was displayed against the dimensionless speed or bearing number. These bearing maps can be seen on the left, with the equation for the bearing number seen on the right, the top right of the slide. The study took into account the coupled fluid structural nature of airfoil bearings, as well as the Coulomb damping effect previously described. The average Coulomb damping in a bearing was given an index value of beta. The resulting force applied on the rotor of the bearings could be given by the equation of motion, which can be seen on the bottom right of the slide. The Coulomb damping in the bearing was calculated through the equivalent viscous damping, which, due to the construction of the bearings and the architecture, is spatially variable across the foil. Therefore, an average value of the Coulomb damping was taken, and this was given the value beta. The equation for this can be seen on the bottom left of the slide. On this slide, we just have a high-level flowchart where we can see the progress of the methodology, as well as the flow of data between the component and system models. To begin with, the bearing map shown in the previous slide was digitized in MATLAB. Following this, a Simulink model was created to represent the bearing and its parameters. The system model was then set up within a multi-body dynamic environment, and the bearing model was interfaced within. When the simulations system are run, collinear stiffness and damping values of the bearing will be determined through the plots. The bearing model will receive the displacement and velocity data of the rotor and calculate the resulting force acting from the bearings of the rotor. The flow of this data will be repeated for each time step during the simulation, and the dynamics of the system over a given time period could be analysed. So to begin with, bearing maps were digitized using MATLAB, as I've already stated. This can be seen on the left, where at the top we can see the bearing maps taken from the original study, and below that we can see the plots digitized within MATLAB. Analytical equations describing the data sets were established. The bearing model can be seen on the bottom right of the slide. The excite data link highlighted in blue, which is where the data would flow into and out of the system model, and the function blocks are highlighted in red. This is where the bearing code was essentially contained and where the analytical equations were kept, and forces could be calculated. Here is a larger version of the bearing model. The black bars you can kind of see on the left and right of the block marked 1, which is the link to the system model, are multiplexers and demultiplexers. These were used to decompose the vector data coming from the excited system model into displacement and velocity and 6 degrees of freedom. And then these were used to calculate the resulting forces within the function blocks using the equation of motion and the analytical equations already established for the airfoil bearings. Here we can see the turbocharger system model, with each body represented as a block in this schematic diagram on the left. These, in fact, were represented by nodal structures, and the link to MATLAB, can be seen on the left of the diagram, was attached to specific nodes on the rotor and housing, where the data would be gathered and the forces calculated. Thrust bearings were also placed in the model to allow stability in the axial direction, as this was purely a radial study. So in terms of the simulations run, the system was run at speeds of between 10 and 110,000 RPM, at intervals of 10,000 RPM, 10,000 RPM to 1,000 RPM, and so on. This was run over a time period of between 0 and 0.15 seconds. The cases of bearing with Coulomb damping index of 0, 1, and 10 were used, as well as a baseline generic rigid surface bearing, which was used as a comparison. In order to establish the role of flexibility and the role it plays in the dynamics of the system, it was modelled as flexible originally, and then a repeat of the beta equals 1 bearing was run in a fully rigid system to allow comparison to be made. So now we can move on to the results generated in the study. So here we can see the peak-to-peak acceleration values experienced over a given time period. So this is purely for the flexible body systems. And we can sort of see an operating envelope generated here with a large peak seen at 70,000 RPM. And this indicates a sort of point of resonance within the system, a critical speed. The reduction in the magnitude of the acceleration experienced can be seen as the value of beta or Coulomb damping is increased. Here we can see waterfall plots which were generated so that the vibration frequencies could be seen at any given speed and the magnitude of which could easily be displayed. Again, here we can see the critical speed of the rotor. It can be identified at 70,000 RPM, which is exhibited as the large spike roughly in the center of the waterfall plot. Again, we can see the magnitude of the excitation being reduced by the Coulomb damping effect. As the index is increased or the value of beta is increased, the magnitude of the resonance is decreased. So interestingly, as we zoom in on the waterfall plots, we can see some non-linear behavior exhibited in the system around between 1,000 and 1,200 hertz range, as well as some subsynchronous vibrations at the lower end of the waterfall plot, between 0 and 200 hertz. And this is evident at all speed intervals. So here we can see a comparison between a rigid body and a flexible body analysis. The rigid body is displayed on the left, and the flexible body system is displayed on the right. A large difference can obviously be seen between these two plots, with significantly less modes of vibration being experienced in the rigid body analysis. The resonant peak, which can be seen in the flexible body at 70,000 RPM, experienced in the previous two graphs, does not appear in the rigid body waterfall plot. Interestingly, the persistence of subsynchronous frequencies in both graphs, so the vibrations at the lower end of the scale, below 200 hertz, are evident in both graphs, which kind of gives the indication that these vibrations actually originate from the bearings themselves rather than the flexibility of the bodies or the bodies themselves. There could be several reasons for this, possibly due to the complex hydrodynamic phenomenon that experienced in the bearings, such as whirl, half-speed whirl, that sort of thing. So now to conclude. So during this study, the concept of co-simulation between bearing maps and flexible multi-body dynamic system has been shown to be achievable. The friction or Coulomb damping effect has significant effects on the system dynamics and cannot be ignored when performing analysis on systems such as this. It's really important to look at the Coulomb damping when considering airfoil bearings. A change in bearing stiffness and damping shows a slight shift in the critical speed or reduction in the critical speed and the size of the magnitude of vibration in the system. The effect of flexibility is not negligible and hence must be included when performing studies such as this, and this is sort of evident from the stark difference between the rigid and flexible body analysis of those four plots. We've seen that the critical speed of the system was located at 70,000 RPM for the current case study and the model used within this. So three major limitations are remaining regarding this. So firstly, stiffness and damping map generator was required for specific bearing would want to be implemented in such a system. And this method is only really applicable after liftoff. So that's kind of after the hydrodynamic air wedge has been generated within the airfoil bearing. And then also the method does not provide the details, any details on the air film within the bearing, such as its temperature or pressure distribution. So now some novelty contributions to knowledge. So using co-simulation to model air bearings as a turbocharger application, taking into account effective frictional damping, has been proved and conducted during this. And this is a novel novel element to this study. Flexible body analysis for turbochargers has only ever really been performed on hybrid air bearings. So using airfoil bearings on the system is unique also. I personally like to express my thanks, finally, in the presentation. I'd like to express my thanks towards my colleagues and their help and support with this project. And on behalf of all the authors, I'd like to thank W.l Heaps GmbH for their technical support and use of models and software during this study. So that concludes the presentation today. I hope people have found that interesting, or at least elements of it interesting. And what I'm going to do now is just return to the conclusion slide, where I have obviously listed the key points of the study and also supplied my email address at the bottom there. So if anybody has any questions, please feel free to direct them towards that email address. Thank you very much for your time today here.
Okay, if any questions, please.
Yes, I do. Professor Heaps, my name is Nong Zhang from Hebei University of Technology. Would you please turn on your PPT on 12, page 12?
Slide 12 was that, sorry?
Your slides,
Yeah.
12, number 12, yes.
Yeah, yeah.
Can you show
So
us?
this is a... Yes, sure.
I want to see your physical model of your rotor and your bearing. Yes.
Can you see that okay?
Yeah, I can see. Now, I would say you have two rotor and you have the, I guess, the turbine wheel. In between
That's
is
correct.
just a shaft. Now, you assume the shaft as flexible or rigid, so you get a different sets of result. Now, where your bearing sits, your bearing is underneath the bearing, there's one piece or two pieces?
So the bearing, there's two bearings in the system.
Okay.
These are connected to nodes on the rotor and the housing as well.
Okay. So what's the distance between the two bearings?
I think it's approximately 10 centimeters. I'll have to double check that though.
All right. Now, I can see your result. If you assume the rotor shaft as a rigid body, then you only get like a resonance frequency almost fixed. But once you assume the flexible, the shaft is as a flexible body, then you do get we so-called critical speed. That's different from the normal resonance frequency, because critical speed is associated with your rotating speed. That's why you also have some nonlinear sort of effect there. Now, when you develop your model, do you assume the orientation of your rotor is always vertically down? The gravitational force is going down.
Yes, that's correct.
So the gravitation force of your rotor provides a sort of a reference for positioning of your bearing working condition. Am I right on that?
Yeah, I believe the model does take into account gravity.
So, for instance, if I turn 90 degrees of your rotor, instead of horizontal but vertical, will your result will be same or different?
Theoretically, they should be the same because the stiffness and damping have been treated the same all the way around in 360 degrees of freedom. So
you do think the mass, the weight of your rotor doesn't matter anymore in your model?
I'm unsure, as this was obviously purely just a radial study. So
okay, so in rotor dynamics, actually the weight of your rotor is a very important factor. So this is okay, Professor Heaps. My question now asked is, since you are talking about this in turbocharge on a vehicle is in motion, vehicle could be in horizontal motion, could be climbing up the mountain, make turns. So the condition of your bearing working condition actually is changing. It's not a
sure.
steady state like what you assume. So
Okay.
did you do any analysis in case the rotor orientation is different from what you assumed? What sort of result you will get?
No, there was no further analysis done beyond this, but obviously for a real vehicle application, you'd need to consider other, like you say, other orientations, also other modes of vibration possibly contributing to the system, such as vibration from an engine.
Yeah, sure. Also, one more factor. Even though if you assume the car is running on the flat road, but if you at high speed, since your rotor is running, rotating at, say, 100,000 RPM, then it's very high speed, right? So your rotor is spinning very fast, and your vehicle is moving as well on the flat road. All of a sudden, your vehicle is not in straight line. All of a sudden, if you turn, when you make a turn, the rotor were subject to a so-called gyroscopic moment. So how do you do that? Did you model that?
So the gyroscopic motion, in the actual study, I've recorded the sort of vibration points of the shaft through the speeds, and this was taking into account gyroscopic motion.
Yeah, I was thinking that would be a critical situation. I'm very interested to know if that happens, will that rotor will damage your bearing? Because there's an airfoil the bearing, your stiffness is not as large as you want. Just throw up some question to you. I'm interested in what you are doing, but I'm also interested to know.
No, that's right. Obviously, if there is contact between the shaft and the bearing housing, it would be quite a bad failure for the airfoil bearing because of its construction.
Yeah. Okay. Thank you. No more.
Thank you very much for your question.
Thank you. Interesting work. Thank you.
Thank you very much.
Okay. If no more question. Okay. Thank you.